Assalamu alaikum. So, welcome to the next lecture. In this lecture, I will continue with the brief introduction of the different controllers. So, today I will start with thyristor control braking resistor, that is DCBR. So, it is again connected in shunt with the line, where here we are using thyristor switched resistor. Again, here alpha is will be, in this case, alpha may be equal to 0 or it may be equal to 180 degrees. So this TCBR is usually used to control or to add the stability to the power system or to minimize the acceleration of a generator during the disturbance. We know that during the fault or during the disturbance, the electrical power is reduced, but when it's connected to the line, there will be some electrical power that will be consumed by this resistance, and the accelerating power will be reduced, and hence the the accelerating power, which is equal to mechanical power minus electrical power. Since electrical power will be there, some electrical power will be there will be reduced acceleration, and hence stability will be improved. So again, this is not the control resistor. We don't have a continuous change in the resistance or continuous firing angle control of the thyristors. We have either alpha is equal to 0 in this case, or alpha is equal to 180-degree case. Here it is slightly different from the inductance, because inductance we have continuous conduction for alpha is equal to 90 degrees, and no conduction for alpha is equal to 180 degrees. But here, in case of resistance, conduction starts from alpha is equal to 0. This TCBR involves cycle by cycle switching of the linear resistor with the thyristor based AC switch with firing angle control. We can use it as thyristor switch braking resistor to reduce the cost. So in this case, we may use the different TCBRs in parallel, so that we can use only this thyristor switch braking resistor, rather thyristor control braking resistor, because thyristor switch braking resistor will be slightly of lesser cost than that of the thyristor controlled braking resistor. Now we'll come to the series connected controllers. We'll first start with the thyristor control series capacitor. So this is known as TCSE. As I have told you, so as I have told you that this capacitor cannot be controlled continuously. It can be switched on or off. It has some problems. We'll discuss it in the coming lectures. So to have the variable capacitance, continuous variable capacitance, we actually use a TCR, that's thyristor control reactor, in parallel with this capacitor, series capacitor. This whole combination is used in series with a line like this TCSE, this point A, point B of this TCSE. So it is a capacitive reactance compensator, which consists of a series capacitor shunted by a thyristor controlled reactor in order to provide a smoothly variable series capacitive reactance. Because when alpha is equal to 90 degree, you will see that whole inductance will come into place, into picture. There will be a combination of this capacitance and this reactance. So if the reactive current is more as compared to capacitive current, the whole effect will be of reactive nature. So if the capacitive current will be more as compared to the inductive current, the whole combination will be of capacitive nature. So depending upon that value, the value of this reactance and the value of this, we can control the value of whole capacitance smoothly. When alpha is equal to 180 degree, no conduction of the TCR, XC will be maximum. In that case, there will be only maximum in the circuit. When alpha is equal to 90 degree, full conduction of the TCR, XC will be minimum, almost negligible, because in that case we design it in such a way, we keep this XC very small as, sorry, XL very small as compared to XC. When this is very small, you will see that since it is parallel, when alpha is equal to 90 degree, it will be as if it is directly connected to this. All the current, almost all the current will be flowing through this. So in that case, XC is minimum, or we can say it is almost negligible. Actually, XL is very low as compared to the XC, so that alpha is equal to 90 degrees, so that when alpha is equal to 90, all the current will flow through the XL bypassing the XC. So no series compensation at that time. At that time, we are saying that there will be no series compensation. As we increase the alpha, the value of this will increase, the value of XL will increase, the value of the current flowing through this will decrease, the current will flow through this, and we can say that the effect of the XC will increase. The reactance of TCR is designed such that it is much lower than the series capacitive impedance, as I have told you just before. Sometimes the inductance will also act as a fault current limiting reactor, because when all the current will flow through this, you will see it will act as an inductive circuit only, and when it acts as an inductive circuit, it will add some inductance to the line. So when inductance is added, you will see that fault current will decrease. One more, Thatcher switch series capacitor. This is again the similar configuration. Only thing is that we have a different alpha. Alpha will be either 90 or 180 degree. There will be no value of alpha in between these two. But in this case, this Thatcher control series capacitor alpha will have a value from 90 to 180 degree. So it is a capacitor reactance compensator which consists of a series capacitor being shunted by a Thatcher switch reactor to provide a stepwise control of a series capacitor reactance. Thyristors are either switched at alpha is equal to 90 degree or at alpha is equal to 180 degree. When thyristors are switched at 90 degree, it will be an inductive circuit, or we can say capacitive circuit. Capacitive effect of the circuit will be negligible. When alpha is equal to 180 degree, it will have only capacitive. Sorry, in this case, it will have inductive uh, nature only. At alpha is equal to 180 degree, it will have capacitive nature. So Thatcher control series reactor. In this case, we are actually using a reactor in series with the TCR. So it is an inductive reactance compensator which consists of a series reactor shunted by a TCR in order to provide a smoothly variable series inductance. In this case again, instead of capacitance, because when you use capacitance over here and then inductance over here, we may have two types of reactance, so capacitive or inductive. Here it will be only inductive. But again, when alpha is equal to 90 degree, only excess is present, that is 180 degree, only excess is present. When alpha is equal to 90 degree, xs parallel xp will be there. So for alpha, between 90 and 180 degree, we have minimum value, that is xs parallel xp, which will be less than xt. Xt will be the total impedance of the whole circuit, that will be less than xs when alpha is equal to 1. So this circuit is not particularly used. It is only used when there is a fault. This is used to limit the fault current and also to absorb the reactive power. If we have more reactive power and we have to absorb the reactive power, in that case this circuit will be used. We may have another uh, configuration of this circuit. We may have a TSR instead of TCR, and then in that case we will be having thyristor switch series reactor, that is TSSR. So again, it is an inductive reactance compensator which consists of a series reactor shunted by a TSR, that's thyristor switch reactor, in order to provide a stepwise control of series reactance. In this case, we have a stepwise control. So sometimes we may have combined shunt and series controllers. In that case, we have thyristor control phase shifting transformer. It is basically a phase shifting transformer adjusted by thyristor switch, because in this case thyristor switch will try to adjust its number of turns, and number of turns are changed, automatically voltage will be changed. So by doing so, we can have a rapidly variable phase angle, because this is the phase shifting transformer. The phase shifting is obtained by adding a perpendicular voltage vector in series with the phase. This voltage vector is obtained by other two phases. So let us say we have this system VR, Vy and Vb. So we are taking a line voltage Vry to this transformer, and we are controlling its voltage through thyristors and giving its output to another transformer which is in series with VB. Now this VB dash, that is the voltage at this output, will be equal to VB plus delta VRY, because this voltage has been taken from these two lines. So let us say this is VR, this is VY, this is VB. So VRY will be this. So we are actually adding this voltage to this voltage phasor VB. Depending, we're not actually adding all the voltage VR or V, we are only adding a magnitude which is very small. You can see this is VB, that is in the same phase, and we are adding delta VRY, which is very small in this. VB dash will be this much. So when VB dash is this much, you will see that VB dash is slightly more than as compared to VB, but there will be a phase shift. Usually in practice, this is usually done in a manner so that this VB and VB dash are kept same. In that case, this angle will be slightly lower than 90 degree. So this is done by the other processes. But even if it is done in this case, this delta VRY is kept very small so that this VB and VB dash are slightly, we can say, consider them to be same, because in that case also VB dash will be slightly greater than this. And in practical purpose, we can uh, uh, consider them to be same, but angle will definitely will change, the angle between these two. So in that case, we can add the phase shift by having such type of configurations, and the magnitude will be decided by this thyristor. Now, thyristor control voltage regulator. In this case, the in-phase voltage is changed. Here, the phase of the voltage is not changed. Here, the magnitude of the voltage is changed. It is a thyristor control transformer which can inject variable in-phase voltage with continuous control. So, for example, let us take this configuration. We have a primary winding of the transformer whose number of primary turns is changed by the thyristors, and when the number of primary turns will change, accordingly this voltage will change. Similarly, you can see this is the same line, same voltage has been taken from this transformer, and it is given to the thyristor combination, and then it is put in series with this. Then you can see this voltage will be added or subtracted by this voltage, but this voltage is again in phase with this because it is taken from the same phase. So total voltage, as we have told you just earlier, it will be equal to, say this is V, this is delta V, it will be equal to V plus delta V. So but they will be in phase. So in this case, voltage can be injected in phase or completely out of phase, depends upon the thyristors what output voltage they will give. Or even if that is not the case, we can change the dot polarity of this. In that case also we can change the polarity of the voltage which is injected in phase. So until now we have all the controllers which were based on the thyristors. We can say they are uh, semi-controlled controllers where we don't have the control over the turn off of the switch. Here we have converter based fax controllers. Actually, these are the controllers which employ the self-commutated switches. This group of controllers basically employ the self-commutated switches. These are basically used to realize the voltage source converter or current source converter, that's VSC or CSC. So in these cases we can use GTO, that's gate turn off thyristors, or we can use the IGBTs for high power usage, or sometimes MOSFET for low power usage. These provide a superior performance characters as compared to the conventional controllers, and same VSI can be applied uniformly for controlling voltage, impedance, and the phase angle. So they have the advantage that only one voltage source inverter can be used to control all the three parameters, that's voltage, impedance, and phase angle. It also enables the exchange of real power with the AC system in addition to provide independent control of the rate to power compensation. So exchange of real power means sometimes we may have the converters, they have the uh, real power source with them. They can supply the real power to the this system, or they can absorb some real power from the system. Usually until now we have seen that only reactive power was exchanged, there was no scope for the real power exchange, but here we can have a scope of real power exchange as well. Now we'll discuss about the first one, that is static synchronous compensator. It is short form and it is known as STATCOM. A static synchronous generator operated as a shunt connected static var compensator whose capacitive or inductive output current can be controlled independent of AC system voltage. So the last part of this sentence is very important. The static synchronous generator. First, I will let you know why it is known as synchronous generator, because uh, we know that the synchronous condenser actually is a synchronous motor that is used to uh, provide the reactive power or to exchange reactive power with the system in the earlier days. That was a good control, and that control was independent of the system voltage. So since this does the same thing, because it controls the reactive power, it exchanges the reactive power without uh, depending upon the system voltage, as was the case for the earlier controllers, which was the capacitance based or inductance based, because they depend upon the system voltage. Their reactive power output is dependent upon the system voltage. So that is why it is, since its reactive power exchange or reactive power output is independent of the system voltage. That's why it is also similar in that sense to the synchronous generator or synchronous motor, or in general synchronous condenser. That is why it is uh, its name has been come as synchronous compensator. Now static has been also introduced to this name because synchronous condenser was not static, that was rotating machine, and we know that rotating machines have their own problem. Since it is only similar in the uh, to the synchronous compensator, which because it provides this reactive power independent of system voltage, so it retains its name. So to differentiate it from the other synchronous compensator, static has been introduced to this, that is static synchronous compensator, and it avoids the problem of dynamics of the synchronous condenser as well. So this static synchronous compensator, you must have now understood where from this name come from. Now it provides the approximate capacitive or inductive current to the to control the actual VR. It's also used to harmonic compensation, because you know that when we use the power electronic devices, there will be some introduction of the harmonics. It is also used to do that. So I will just try to introduce you. You can see this is a capacitive DC link. Actually, this is not used to provide, this capacitive DC link is used to provide the inductive as well as the capacitive current to the system. It will draw inductive as well as capacitive current. What it actually does, it will provide the current, because that is all inherent to this control, the control of the switches. So it controls the switch in such a way, if it has to draw the capacitive current, it will see the voltage and it will draw the current in such a way so that that current is leading to that voltage by 90 degrees. So that is done by the control, and that part which we'll be discussing in the coming chapters, in which we will discuss the static synchronous compensator. But I just want to try to make you sure that we don't have actual inductor and actual capacitor to do the actual thing. We have only the effect of the capacitor or inductor. Effect means that we are supplying the we are drawing the current that may be leading to the voltage by 90 degree or lagging to the voltage by 90 degree. When it is leading to the voltage by 90 degree, it will act as a capacitor. When it is leading to the voltage by 90 degree, it will act as an inductor. Since I have told you that it does so independent of system voltage, it only takes the voltage as the reference and sees its magnitude. If the magnitude is less, automatically reactive power has to be supplied. So it supplies the reactive power as per the demand. So that is also done by the control of these switches. We'll see that in the uh, in the chapter when we discuss the statcom. For the time being, I think this is enough for today. We'll discuss the other controllers in the next class. Thank you.